Hello everyone, my name is Will Cully from Cornell University, and in this video I will go through the pre-analysis for steady flow in an artery. In this problem, we will be looking at the carotid artery, which helps to supply oxygenated blood to the head and neck. We will use the geometry shown here. To get a sense of scale, the diameter of the inlet is 6.3 millimeters. The working fluid will be blood with the shown material properties. We want to simulate the flow with a Reynolds number of 600. So, using the provided properties, we will pick an inlet velocity of 0.315 meters per second to achieve this. Finally, we have the specified outlet pressure shown here. We will use these parameters to investigate the resulting pressure, velocity, and wall shear variations inside and along the walls of the artery. We will interpret the solution process using this Blackbox framework. We start with our physical problem, which in this case is flow in an artery. From this, we can use physical principles and assumptions to create a mathematical model inside the fluent black box. It figures out this model from our user inputs. Let's take a look at the mathematical model. This consists of governing equations and boundary conditions. For governing equations, we first have the continuity equation, which is conservation of mass applied to an infinitesimal fluid element. It is shown here in terms of derivatives of the velocity components. Next, we have conservation of momentum equations, which arise from applying F equals ma to an infinitesimal fluid element. Since our flow is three-dimensional, the acceleration term will have three components, corresponding to the three coordinate directions. This means we can produce three equations. These equations are shown here. From these equations, our unknown functions are u, v, and w, our three velocity components, as well as the pressure. Each of these are functions of the coordinate location x, y, and z, meaning they can vary spatially. We also have assumptions built into our mathematical model that affect our governing equations. Firstly, the steady assumption means that there is no time variation of the flow properties. This knocks all of the time derivatives out of the governing equations. These have already been omitted above. Additionally, the laminar assumption means that there is no turbulence in the flow. This means we do not need to add any terms or equations to account for that. Similarly, we will assume that the flow is incompressible, meaning that the density is constant everywhere. Finally, we will assume that the working material behaves as a Newtonian fluid. Note that blood is not strictly a Newtonian fluid, but it will be approximated as such for our model. All of these assumptions are built into the governing equations shown above, and we will ensure that they are correctly provided to the solver. In addition to the governing equations, our mathematical model includes boundary conditions. The domain of our boundary value problem is the fluid region inside of the artery. The single opening on the left side will be our inlet. We will specify the velocity normal to the boundary to be 0.315 meters per second, as mentioned before. The next two openings on the right side will be outlets. We will specify the same pressure condition at both outlets to be 13,332 pascals. Finally, along the outer walls of the flow domain, we will specify that the velocity must be 0. This is equivalent to enforcing both a no-slip and no-penetration boundary condition. This completes our overview of the mathematical model, so we can now take a look at a brief overview of the numerical solution strategy that will be used to obtain values of our unknown functions in the domain. To begin this process, we need to divide the domain up into multiple control volumes, or cells. This image shows a photo of a sample mesh of the flow domain inside the artery, with each of these shapes being a unique control volume. Since the domain is 3D, the control volumes will be 3D as well, as shown in the cells highlighted in green here. To simplify this for the explanation, we can instead consider an analogous 2D geometry shown here. From this mesh, we will determine values of unknown functions at the center of each of these cells. This value will be an approximation of the average value of the cell. For other regions not in the center, we can approximate its value by interpolating between cell center values. This means that anywhere in this cell, even on the boundary, these values can be interpolated from the value at the center and other neighboring values. To get these values, the Fluent solver will derive algebraic equations relating the primary unknowns at each cell center to the neighboring values. This will create a system of equations. The solver will then invert this system to obtain the cell center values. Importantly, the solver only directly determines values of our unknown functions. All other quantities and visualizations are post-processed from these values. To develop and solve these equations, Fluent uses the finite volume method. It starts with the mathematical model, which we know is the differential form of our governing equations and associated boundary conditions. It needs to develop algebraic equations relating cell center values of the primary unknowns. To do this, it first goes to the integral form of the governing equations and applies it to each control volume. The process of developing these algebraic equations introduces a discretization error caused by only finding the values at cell centers. We can reduce this error by refining the mesh. These algebraic equations are nonlinear, so to solve them, Fluent must linearize them about guess values. Doing this introduces a linearization error. This process is performed iteratively by continuously updating the guess values. We repeat this process until the imbalance falls below a selected tolerance. For more information about this process, check out the E. Cornell certificate for computational fluid dynamics. Back in our Blackbox framework, we have discussed the mathematical model and the numerical solution method, and how that produces the selected values at selected points. Now, I want to show some expected trends to help us gain a better understanding and intuition about flow in the artery. Here's a schematic of a top-down view of the artery. The inlet and outlet boundaries are labeled. The first key location to investigate will be the branch section. As the flow approaches this, we can expect a region of high pressure and low velocity as the fluid is slowed down at this stagnation point. Another key location is along this bulge on the path to outlet 1. We can expect to see some flow separation in this region. This means that this section of the flow will not follow along a direct path to outlet 1, but instead the boundary layers can separate, causing a low velocity region in which the fluid will recirculate. We can also consider the expected velocity profiles as we move along the artery. At the inlet, since we specified the velocity as a boundary condition, we can expect a constant speed flow along the width. As we move downstream, however, boundary layers will begin to develop because of the no-slip condition along the walls. This means that the velocity will slow next to the wall, and this low velocity region will grow over time. We can expect this to effectively round the velocity profile as shown here. If this artery section was long enough, we would expect this to continue until the boundary layers meet in the middle and the flow profile becomes parabolic, as is characteristic of flow in a pipe. As we move into the outlet branches, we can expect the velocity profiles to change and be slightly skewed towards the inner edges. This is because of both the stagnation and separation regions. Estimates of these profiles are shown here. Finally, we expect the fluid to move along both of the two branches. We do, however, expect more of the fluid to exit through outlet 1. More specifically, comparing the outlets using the mass flow rate, we expect 70% of the total mass flow rate to leave the artery through outlet 1, while only 30% leaves through outlet 2. For more information on this observation, or any of the information presented above, please consult a textbook like the one mentioned here. This completes the pre-analysis content, and we will now get into the simulation.